Good morning. Today is the lecture number 6 of this module Robot Dynamics and Control. This is the last lecture of the module Robot Dynamics and Control. Okay, so let us see what we have seen in the last lecture. We had done something about Lyapunov theory. So far we have been studying Lyapunov theory. We have applied it to robot manipulators. First PD control, point to point regulation type of a control, and then in the tracking control. So we have given the tracking result only, so we will do the analysis of the tracking part today. Okay, so some analysis of the tracking part we will see today, and then we will move on to force control. Okay, so that is kind of a recap and what we will see in the today's class. So the stability analysis of the tracking controller that we have presented in the last lecture. Okay, we have seen this Lee and Slotkin kind of a controller in the last lecture. So this stability analysis will carry out in today's class. And before that, we'll just revise some of the fundamentals of Lyapunov theory again. It is kind of a new topic, so we'll just do the revision, a little bit revision of Lyapunov theory again. And then we'll move on to force control. In the force control, there are many strategies available. What we are going to look at is this strategy, stiffness control and impedance control. And there is something called hybrid control, where you control the force and position together. That we'll see, if time permits, we'll have a look at that in the next classes. Okay, so to just recap Lyapunov theory fundamentals. So basically Lyapunov captures the stability of the system in terms of some functions called Lyapunov function or Lyapunov function candidate initially. Okay, this is a picture of like schematically what is happening in the Lyapunov analysis. So you have this energy based or energy kind of a function which is positive definite, and then you are having a look at the solution trajectory, the derivative of this function along the solution trajectory. This is a solution trajectory, and we see that if the derivative is continuously decreasing, that means the solution trajectory is having a behavior somewhat of this kind. So along this V, the solution trajectory, along the solution trajectory, the derivative of this V is continuously decreasing. That means you are coming down each level on this V, and then because this is a positive definite function, you are driven towards the origin when V dot is decreasing. Okay, so that is what we saw. So there is a strong correlation between the energy based or some Lyapunov function or some positive definite function and its derivative, the properties of this positive definite function and its derivative, and the stability of the system. Okay, so this is a basic fundamental understanding of Lyapunov theory. Okay, so do you see that? See, this is very strong, like important to understand this point. Okay, so once you understand this, then it is apparently clear, like the theorems that Lyapunov has presented. We need not go into all the mathematical details, but we can appreciate why the conditions on V and V dot are there. Okay, so let us have a look at again the one of the theorems, which is asymptotic stability theorem. So the theorem says that equilibrium is uniformly asymptotically stable if there exists C1 decrescent LPDF. These are the three properties V has to satisfy, and such that V dot is negative definite or minus V dot is LPDF. Okay, so this C1 decrescent LPDF V can be schematically represented in this fashion. It is bounded above by class K function and bounded below by class K function. Okay, Now let us move ahead to our tracking problem. Again, recall what we are talking in terms of tracking problem. We are given a trajectory to be tracked, okay, some straight line or some curve which function is predefined, okay. So based on this trajectory to be tracked, we find out the joint trajectory, the desired joint angles, okay. So all the manipulator angles should be moving along these desired trajectories so as to realize this trajectory at the end effector. So we find out this joint angle desired trajectories, and then our task is to drive the manipulator along these desired joint angles, okay. And then this is in terms of time t, so it is a function of time. So we need to make sure that at a given time all the joints are at their desired locations, then only the end effector is going to move along the desired trajectory, okay. So that is what our tracking problem is. And then now we will see the application of this theorem, which is the asymptotic stability theorem, with the controller which we have seen in the last slides in the previous class, okay. That controller will apply this theorem and see how the controller is functioning, or how if we can reach some result in terms of a Lyapunov stability for the tracking controller, okay. And again, recall that you cannot apply Lasalla's theorem in this case because it is time varying system, okay. If system is time invariant, then you can apply Lasalla's theorem. There is one more class where, like, if the systems are periodic, then also you can apply Lasalla's theorem. There is slight variation, but in general when it is time varying system, you cannot apply Lasalla's theorem. So we have to restrict ourselves to whatever other theorems that are there. We cannot apply Lasalla's theorem, okay. So either you can use Lyapunov tools, or you can use some more advanced tools which are based on the LP spaces. So we will not go into details of those tools, but you should be aware of, okay. So let us see our previous tracking controller again. We have defined this controller in this fashion. So why we have defined it and all those details they will be clear now. So this is A is this new dot, and then this is given by this function, okay. So it has in some sense this desired trajectory derivative term. So this is d times this term is in some sense your computed torque, if you recall the inertia part of the computed torque. Similarly, c times this qd dot term will be again in some sense your computed torque, okay, or the c part of the computed torque trajectory, okay. But in addition to that, you can see that there is this error term which is added in both of these, okay. So this additional term will take care of the thing we'll see as we go along, but this is in some sense taking care of no need to apply Lasalla's theorem, okay. We will get asymptotic stability result directly by applying Lyapunov theorem without going to the advanced tools, okay. We will see that how that happens here, okay. So this controller is developed by Lee and Slotin, and it's developed around 1987, okay. So let us see the analysis with this controller. Now recall our previous classes, the equations of dynamics of the manipulator. In terms of joint variables, it was given in this form. This J is the inertia of the motor which was transferred to the joint. Okay, so this is our equation of a manipulator. Now this term I have renamed it to be D1 here, just for the convenience, so that I can call this whole term as a D and preserve our basic form of the equation. Okay, so this D is nothing but D1 plus this J. Okay, and still now our condition that D dot minus 2C is Q symmetric matrix will be preserved, because this J is a constant inertia. So when you take a derivative, that will go to 0. Okay, so now we'll substitute in these equations your control law that we have just presented in the last slide. So this D times A, which was Q D double dot minus lambda into E dot plus C plus B into this term nu minus KD into R term was there. This R we have seen here to be E dot plus lambda E. Okay, so this gives us this equation. Now we simplify that by bringing these terms on the other side. So you get here Q double dot minus QD double dot plus lambda E dot, and similarly these terms, which finally results into this equation. Okay, so we term this variable R, I mean we write the equations in terms of this variable R now, and then they will become as simple as this form. Okay, this R is E dot plus lambda E. Okay, so this is a form of a equation which we have to analyze for asymptotic stability with the error dynamics. Okay, R is basically representing the error dynamics. Okay, it has both error derivative and actual error E and E dot. It is a function of E and E dot. Okay, so in terms of this new function R, we have this equation of dynamics, equation of error dynamics appearing over here. Now we need to prove by using Lyapunov stability theory that this indeed gives us error and error derivative both going to 0 as time tends to infinity. So how do we do that? So we have to select first a Lyapunov function. So selection or choice of Lyapunov function will be usually energy based. Okay, in this case, since R is a new term or a new variable for error dynamics, we choose the Lyapunov function to be in terms of R. Okay, so this is not just dependent on error, this is also dependent on this is not just dependent on error derivative, but also dependent on error. Okay, this term, and in addition this is kind of a spring energy that is there because of this part of the term. So Kd into lambda is basically spring constant when it is multiplied by E. You can recall your standard spring mass system equation and compare this term, and then you will see that is kind of a spring term in the simple spring mass system. Okay, so corresponding to that, the spring energy is getting added here. Okay, now we'll have to first see whether this is positive definite function or not. Okay, so let us expand this in terms of error. Now see, we want to see this as a function of error dynamics as a positive definite function. Okay, so our all conclusions are basically about error dynamics we will have to conclude. So we have to see in terms of error whether this is a positive definite function. See, in terms of R, it's clearly the positive definite function here and here. Now in terms of error also we can prove that that is true. Okay, so we just expand these by substituting for R as E plus lambda E. So this is E plus lambda E transpose T times E dot plus lambda E. Okay, so this R is E dot plus lambda E. So you take this transpose inside, you get this equation, and then you multiply. So this E dot transpose times dE, the first term, then this E transpose lambda transpose into d lambda E, this multiplied by this, and now this cross multiplication terms E dot transpose d lambda E and E transpose lambda transpose d E dot. Okay, now these both of these terms, since these matrices are symmetric positive definite matrices d and lambda, because of that both these terms will turn out to be the same. Okay, so you can just write this as twice one of these terms. So how does V look like now? So it has, I have put this, substituted this as per our previous expansion, and then you will find that this can be simplified in this fashion, like you collect the terms corresponding to E dot square or E transpose d E dot, E dot transpose d E dot, and then this is a term corresponding to E transpose something into E. So this part is also added over here. Okay, and this term is represented in this. Okay, and then these two terms are twice one of these terms, and multiplied by half is this term over here. Now again we can put it in a quadratic form in this fashion in terms of this matrix. Okay, so here this is half lambda transpose d lambda plus lambda kd matrix. This is lambda transpose. See, these are two equal terms, and then this is half d, which is a term corresponding to this. So this is a quadratic form, and now we have, for this form to be positive definite, we know that we need this matrix to be positive definite, this first matrix, and then we need the determinant of this entire matrix to be positive, and then if you multiply and see, it is indeed the case. This term is getting cancelled, this term multiplied by this term is getting cancelled with this term multiplied by this term. Okay, because of that this is a positive definite. We can conclude about the positive definiteness of this entire matrix. Okay, now let us see how we can take a derivative and then see what is a property that V dot satisfies. Okay, so let us have a look at equations again. So v dot, v is this form. Okay, now we'll use this form for taking the derivative. So it is half 2 times r transpose d r dot. So see, this and this r, they both are differentiated, and see, these are the, this is a product of 3 terms. So we have to differentiate one at a time. Okay, and then again using a symmetry property, you can write this as 2 times r transpose d r dot. Okay, and then this is r transpose d dot r term. Okay, and here it will become 2 times, I'm sorry, the 2 is missing in this part. This will become 2 times E dot transpose lambda kd E dot, E transpose lambda kd E dot, or E dot transpose lambda kd E. Both are the same terms because of the symmetry property. Okay, now this r dot or d times r dot, you recall from the previous case, our basic equation. This is just the negative of c plus b plus kd times r. Okay, so I have substituted that in this equation. So 2 times r transpose c plus b plus kd times r for dr dot, and negative sign over here, and other terms are as they are. Now you can see that this d dot minus 2c can be separated out. From this equation you have this 2c here, and here we have d dot, and r transpose and r, they are same, r transpose and r. So I have separated out this term d dot minus 2c multiplied by this half over here. Okay, and then all the other terms are remaining as they are. Okay, now we know that this r transpose d dot minus 2c r is equal to 0 because of the skew symmetry property of this matrix that we have seen in the earlier classes. Okay, this d dot minus 2c is a skew symmetric, so quadratic form with the skew symmetric matrix will have 0. If you evaluate that form, it will be 0. Okay, so we use that property here. So that is why now again I am emphasizing that property, skew symmetry property of all the robotic manipulators, is very important, because it helps you doing this analysis over here for tracking cases also and regulation cases also. Okay, so you have to use that skew symmetry property for stabilization, like our proof of stabilization. Now let us proceed and see what it results into. So you have this E dot transpose. Now I have expanded this R in terms of E dots, and its basically definition. So this is E dot transpose, E transpose lambda transpose B plus KD into, again R is E dot plus lambda E. Okay, and then this term 2 times this remains as it is. Now if you expand it further, you see that these terms are getting cancelled with each other. Okay, you have expanded this part. Okay, and then you see E dot transpose KD lambda E, E dot transpose KD lambda transpose KD E. They are both are the same terms. Okay, they are equal to 2 times E dot transpose E transpose lambda KD E dot. Okay, so do you see that? Because of the symmetry property of these matrices KD lambda, I can have this result. Okay, though you have in some cases E dot here and E dot here, you can still, that property will be, because of the symmetry, that property will be valid, like you can still write it as a 2 times one of these terms, and then this term and this term will get cancelled out. So what we get now is this part. So if we write now again, see this term is a first term, this term I have written it first here, then this is whatever is remaining after cancellation is b times lambda, and then E dot transpose, this is the first term here, this is the term, okay, that appears over here. Now this again can be written as a quadratic form, okay. So in the quadratic form, this is the first term, this b times lambda, this is 2 times b lambda coming here. So this b times lambda will appear equal terms in both these places, cross diagonal terms, and then this term corresponding to E dot, okay, and then this is a negative sign taken out of all these terms. Now I need to prove now that this particular matrix is a positive definite matrix. Then I can have this result. Since this is a negative sign over here, I have a result, I will have a result of the asymptotic stability. Okay. Now to see that, we will first consider this part. Since it has all the positive definite matrices, lambda, b, kd, they are all positive definite symmetric matrices. Because of that, this matrix or determinant of this matrix is also positive. Okay. So this matrix is positive definite. Now if you see this here again, like if you see the product of these two terms minus product of these two terms, the first term here will cancel this product, okay. So lambda transpose b lambda multiplied by this b will cancel b lambda and b lambda multiplication. Again recall, lambda is a positive definite symmetric matrix, okay. Because of that cancellation, now what we remain, what you get here is, for the determinant, is only the determinant of the matrix, which is again a combination, okay, of some positive definite symmetric matrices, and that's why it comes out to be positive definite. So that's how we conclude that this entire matrix here is a positive definite. Because of that, now we have our result, like C1 decrescent LPDF, or in this case it's a PDF function V, such that this negative of V dot, which is now this matrix in the quadratic form, is positive definite, PDF. So we have the asymptotic stability result by the way of Lyapunov theorem on asymptotic stability. Okay. So this is how we reach this asymptotic stability result. Now what this asymptotic stability means is, your E and E dot are going to go to 0. This is the error which are going to go to 0. Now if you recall the definition of E, it's nothing but Q minus QD. Okay, your actual joint angles minus the desired joint angles, that is the error that you define. So that will also go to 0, Q minus QD will go to 0, which means like your joint angles will go finally to desired joint angles as time t tends to infinity. Okay, so that is how you interpret this asymptotic stability result. Okay, so we have this tracking controller, which is very high performance tracking controller. If you implement this, you will see that like very clearly that if you set the gains appropriately, then immediately your actual trajectories will converge to the desired trajectories with this tracking controller. Okay, so if you compare the results of this simulation with your corresponding computed torque control strategy, you will find significant improvement for this controller. Okay, so it is very high performance kind of a tracking controller that we have. Okay, now let us just recap what we have seen so far. We have initially started with the PD control, point to point control or regulation result. Okay, so PD control for regulation purpose to move manipulator from one point to another point. Then we introduce feed forward computed torque strategies, basically for trajectory tracking application. We didn't do much of the analysis of these, but we have seen that these controllers will result in better tracking performance than just a PD controller. Okay, and then we moved on to this trajectory tracking controller given by Lee and Slotin. Okay, see, there are n number of different types of controllers available for robot manipulators, but these are only some of them. Like it is not possible to cover all of them in this class, but these are some of the very basic ones. Okay, you should be aware of these, and then like more sophisticated can be built based on this knowledge. Okay, so whatever insights we have got based on these whatever controllers we have seen so far, that will help you understand like more sophisticated versions of the controller. Okay, now these other controllers are like, one is inverse dynamics control, and then inverse dynamics with robustness. These are again some of them, not all, but these are the controllers. Now we have restricted so far our attention to control involving only the trajectory tracking or trajectories, like moving from end effector from one point to another point. Okay, but there are many applications which require like not just this movement, but to control the force that robot applies at the end effector while handling something. Say for example, if you want to like pick up egg, you want to pick it up by the robot manipulator without breaking it. So there comes the significance of control of the force that robot applies on its environment or objects it handles. Okay, so that is another thing that we'll see some insight. Again we'll get into the force control. We'll see some details about the force control now. Okay, so what is the basic need of the force control? I'll explain you first that thing with couple of examples so that you can appreciate why we should really go for force control. Okay, so whenever the robot is interacting with the environment, that time the force control becomes important. When it has to move one thing from from one point to other point, a thing, any object from one point to another point, without having to bother about if there is anything else the object is interacting with, then it becomes a purely a regulation or trajectory tracking kind of a problem. Okay, but when now that object is say stationary, and say for example robot has to paint something, okay, by brush, so there is a interaction between the environment and the end effector of the robot, then the force control will come into picture. If it has to wipe something, then it will come into picture. So we will see the application details and how what is happening in these applications in a while. And then there are different types of force controllers that we are going to see in this class, which is first is stiffness control and another is impedance control. Okay, so we'll see why these ideas of stiffness and impedance control come into picture. So as we have seen, position control can be used only in the cases where the manipulator is not interacting with the objects in the workspace, or there is no constraint on how much force it applies to the objects while moving it. Okay. Say if it has to move pieces for assembly purpose, okay, the rigid pieces for some assembly purpose, then there is not much restriction on the force that manipulator applies on these objects. Okay. So in that case, I mean, you don't need very sophisticated kind of a force control strategies to be implemented. Okay. But when there is a interaction, as I said earlier, whenever there is a objects are soft and you don't want to break it by application of gripper forces, that time again like this force control will come into picture. Okay. Or if robot has to carry out any screw driving application, okay, then this will come into picture. Okay. So suppose another example is washing a window or wiping the window. See, there is a car, like car assembly line, in which finally everything has been done, and now robot has to give final wiping of the glasses of the car or windows of the car. In that application, it should not apply force more than a certain value, otherwise it will break the glass. Okay. So how to achieve that? It's not just a tracking, like you see, if we apply only tracking controllers in these cases, will they work? Okay, we'll see what is the problem if we apply only tracking controllers. Now if robot has to write with the flat tip marker, okay, write some number or something on the component, again it has to worry about how much force it is applying to the tip. Okay, otherwise things will get damaged, like I mean it will result into damage. Okay. So what is the effect like if we do trajectory tracking control alone in these cases? Okay, will they work? What will be the problem if we apply only the trajectory tracking control? There is no concern about force. Okay. Now you see that if we deviate slightly from the trajectory, then it will result in either losing of the contact with the surface, or it will result in the excessive forces applied to the environment. Okay, we don't want either of these things to happen. That's why like we have to go for some active strategy which will involve, I mean which will have some consideration to the force. Okay, do you see that? Okay, now let us see how we can do that. So we will have to modify our control command so as to take this effect into account. Okay, effect of object touching the environment. So how do we modify our control such that this thing is accounted for? So any schemes or ideas you can think? See, it is like when we are interacting with the environment, what we do, you just think about that and then you will get many ideas how we can do that. Say for example, we have to pick up some egg from a basket. What way we go about doing that? What is happening in our mind when we are picking up the egg? We sense in some sense the force. Okay, so with the distance, like as end effector goes closer and closer to the object, we slowly decrease the force or like try to see what force we are applying, and then based on that we take decision how much more force to apply or not. That is kind of thing that is happening. Okay, but how do we keep this kind of a knowledge in the controller of the robot. Okay, suppose it is given that, say for example, I know what force I should apply to the egg while picking it up. Then how do we use that information to control the end effectors of the robot to not to exceed the applied, the required force. Okay, so that is a kind of a idea that we have to think what schemes we can use here. Okay, one is like you can use more sensors, like you can use force sensor or tactile sensors, where you can know like how much force you are applying, and based on that you can make a decision. But suppose we don't have force sensors, like force sensors are typically very costly to implement. So if we don't have force sensors, then what is a way, what is the best thing that we can do? So let us see one idea based on the stiffness and compliance. Okay, so if you see by design, all the robots are very rigid. Okay, so we provide a device in the robot. Okay, this is a virtual device, to say, by using what you have is control action. Okay, so this device is a spring, virtual spring and damper kind of a system. So imagine that, like, now instead of robot end effector directly touching, there is some spring and damper in between. Now if we control the position, then how much after the spring is touching the object. See, after spring has touched the object which we want to pick up, now if we change the position, control the position, then we can control the force we can apply to the robot, because force will be the spring compression multiplied by spring constant. So the spring compression will be able to control by controlling the position. So that is the idea. So we have in control law a term which is corresponding to the spring kind of a behavior, and then we have a position control strategies. Okay, so that is the idea that is used in the stiffness and compliance control. So the advantage is, like, you just need to have a control over the position, and then you can control the force. Okay, now let us see, I have this illustration for this idea. Say you have this end effector here. See, it is at this point it is touching the environment. Okay, now if we move the end effector a little bit, then it is going to compress the environment. Okay, now let us assume that our environment is very much rigid. Okay, when robot applies force to the environment, it will be the balance between the forces, like reaction force produced by the environment, and because of that, there is, if there is some finite stiffness to the environment, okay, that environment or that object is going to get deformed a little bit. Most of the cases it will not get deformed to a great extent, unless it is kind of a sponge that you have to pick up by the robot manipulator. Okay, so you see the difference between these, like, two cases where you have to pick up soft objects or you have to pick up hard objects. Okay, usually most of the applications you will find that these robots are picking up hard objects, so the environment is pretty stiff. Okay, then now this is like the trajectory along which we want our manipulator to apply a specific finite force. Okay, like, see, this is the environment information, like environment has this kind of a trajectory, and say it is a glass window on which robot has to apply a finite force for wiping it out, okay, or for some other application, whatever it is, okay. So it has to move along this trajectory and apply some finite force, okay. Now the idea of the stiffness control is you define a parallel trajectory inside. So corresponding to this xe point, there will be xd point inside the environment, okay, and command your robot to move now along this trajectory with the kp kind of a control or spring effect, okay, proportional control. Then what will happen? See, robot is trying to reach this point D, but once it reaches this xe point, it touches the environment. Now it cannot further move, but it will still keep on applying the torque corresponding to the error, which is xc minus xt multiplied by the proportional gain to the motors. So it will keep on applying that much torque, which will correspond to, in some sense, applying the force. Do you see that how this stiffness control works? Okay, so that is a basic concept or basic understanding, fundamental understanding for the stiffness control. You have to command robot to go along a trajectory which is inside the environment. Okay, so corresponding to these xc minus xt points, xd error, the proportional control or control torque will be applied, which will be resulting in a force, desired force in the environment. Okay, now let us see the detailed computations for some N-link manipulator. How do we do that? So this is the basic idea, fundamental idea about stiffness control. Now in case of n degree of freedom manipulator, you can design the similar scheme, okay. Suppose your desired stiffness is chosen across each degree of freedom. See, end effector has 6 degrees of freedom, so you can select your stiffness along each of these 6 degrees, okay, and then correspondingly you can get the torques or whatever. Okay, so this stiffness matrix can be specified as 6 by 6 matrix Kx. Okay. Now the desired restoring force for virtual displacement. Now suppose virtual displacement delta x is given to the end effector into the environment. Okay. Then corresponding to that virtual displacement, there is this force Kx into delta x, that will be a virtual force or restoring force. Okay. Now see, why we are doing all this computation is basically we want to know how much torque we should apply at our joints, or how much, what is the scheme to apply the torque at the joints, so as to produce this type of a force or this type of a stiffness characteristics for the end effector when it starts interacting with the environment. Okay. So we are, after that we convert now this delta x by using Jacobian to delta q in this fashion. So delta x can be represented in terms of delta q by using this Jacobian matrix, and then this torque in a similar fashion is related to the force with this Jacobian. Now this force again we replace with Kx into delta x, that is our desired force, and then this delta x is nothing but J into delta q. So J transpose Kx into Jq is now desired stiffness of the joints. Okay. So this tau is nothing but this desired stiffness multiplied by joint displacement delta q. You all see that? So this stiffness matrix at the joint can be obtained in this fashion. Now if we have a control law that this stiffness matrix multiplied by the error, okay, then it produces the desired force or stiffnesses at the end effector along each of the degrees of freedom. Okay. So this is the basic idea about stiffness control. Now let us see just some gist about impedance control. Now impedance control basic idea is to define a mechanical impedance in this fashion. It is a ratio of force versus velocity, okay, and then we specify the desired impedance in this fashion. So this impedance concept is basically similar to impedance in the electrical domain, okay. So corresponding elements like we have spring for the stiffness control, it's again like we can have that stiffness control visualized as a special case of this impedance control. So that is the idea here, like you can generalize that. I'll show you how exactly this stiffness control is a special case of impedance, but basically you specify this desired impedance. In the case of stiffness control, we don't have these terms x dot and x double dot and x dot. We just specify that your external like Fe is equal to k times x. So k is a stiffness that we desire, okay. So that is how, like in some sense, we'll come to that again little later. And then you design a controller which achieves this kind of a impedance when interacting with the external environment. Now notice that your dynamics of robot which is interacting with the environment, it will change in this fashion. You will have this term J transpose Q into the Fe, which is the force of interaction with the environment, appearing in the robot dynamics equation. Now let us not go into detail how we can design this controller and how we can go about. You can use whatever tools we have seen so far, and we can design this kind of a controller which will give finally Fe equal to this kind of a relationship. Okay, so you have to choose this control U, maybe compensate for these terms and whatever, like you do computed torque kind of a compensation, inverse dynamics kind of a compensation, and then finally your equation should remain of this form. Fe is now this much. That is how you have to design this controller, okay. So we will not get into details, but this is a basic idea about impedance control, okay. So let us see some physical insight. Say if we have a stiffness control, it can be, as I said earlier, it can be considered as a special case of the impedance control, okay. Now you see that this special case is when x double dot and x dot they are 0, okay. In the previous equation we have seen, and then that means that it is a steady state kind of a analysis. So if we consider only steady state force, no dynamic forces in the impedance control, it will become similar to stiffness control, okay. Now when the end effector is moving freely, there is no interaction, that means the impedance is 0, okay, or there is no resistance or from the environment, okay. So that is a 0 impedance case. So that is how one can interpret physically the impedance control action, okay. So both like pure position control and pure force control cases, they can be considered as a special cases of the impedance control. Now what we have seen is these two types of force control strategies. Now there are some implementation issues that are, I just want you to be aware of these. So stiffness control was similar to PD type of control, so it is very simple to implement, and but only thing, instead of in the stiffness, whatever calculations we had to do in the stiffness, I mean in the PD control, we have to do more calculations in the stiffness kind of a control. We have to do this Jacobian or this stiffness transformation calculations. Okay, and this tau b is a torque which we can add some damping into the system or something of that sort we can do to have the addition, or this just make simply tau b equal to 0, that will also do. Okay, and then in the impedance control, implementation is more complex. Typically, like you will find that control now will be more complicated in this case, and control is not robust in the impedance control case. Okay, so in summary, what we have seen today is basically Lee and Slotin kind of a control algorithm. We saw the Lyapunov analysis, how we can find out V, V dot, and conclude about the stability of the Lee and Slotin kind of a controller. Then we have moved to study little bit about fundamentals about the stiffness control and impedance control for force control strategies. Okay, and in the next class now what we will see is more futuristic topics in the robotics. Okay, we will study little bit about micro electromechanical systems and how they are useful for robotic applications and futuristic robots.